Hey everybody, we are going to start the renal system today. So I'm going to break this lecture up into several parts. This first mini lecture is going to cover waste products, where they come from, and how we deal with them. So that's actually going to lead into one of the major functions of the urinary system, which is waste excrement. So I'm going to be using my iPad to write on. So this will be more like a Zoom lecture than like one of my typical videos. So you'll be able to write along with my notes. Okay, so we're going to go ahead and get started with waste. When we have a biological molecule like carbohydrates, proteins, lipids, or nucleic acids, we break them down, a lot of times for energy, and they produce products, and many of those products are waste products. We are most familiar with carbohydrate metabolism. When carbohydrates are broken down, the products are CO2 and water. Water ends up being just part of our fluid, and CO2 is a waste product that is primarily excreted through the respiratory system. So what happens when we break down a protein or a lipid or a nucleic acid? What do we make? Well, we make CO2 and then some other things as well. So let's make a table that lists the various biological molecules, their waste products. I'll show you some images of those waste products, and then we'll move into kind of a tangential topic that's super important called acidosis and two different types of acidosis. All right, let's get started. All right, so let's go ahead and list our four major classes of biomolecules as covered in the workbook. We have carbohydrates, proteins, lipids, and nucleic acids. Okay, so when we break down carbohydrates, the major waste product is CO2. Again, water is a product, but I wouldn't call it waste. We know that the primary system that is responsible for the excrement of CO2 is the respiratory system, which we just finished covering. It turns out that there's actually another system that can tangentially assist in the excrement of CO2, and that is the urinary system. Does CO2 directly diffuse into our urine? Not exactly, but remember, most of the CO2 in our blood is transported in the form of bicarbonate, and bicarbonate can be excreted. So you can actually assist with CO2 excrement in the urinary system. So I will change the color to denote a secondary assisting system. All right, so proteins, lipids, and nucleic acids all produce CO2 as well. In addition, they'll produce at least one other waste product. So let's list those out. So we have CO2 for all of these, but proteins need to get rid of the extra nitrogen, and they do so by making urea. And if you sense that the word urea and urine sound awfully similar, you wouldn't be off base. Lipids produce a group of molecules called ketone bodies. And nucleic acids produce something called uric acid. Okay, the primary site of excrement for all of these is going to be the urinary system. So the urinary system is the primary organ system that deals with the excrement of urea, that deals with the excrement of ketone bodies, and deals with the excrement of uric acid. So obviously one of the major functions of the urinary system is going to be dealing with waste products. Now, let's take a look at the structure of some of these waste products. So we have on the screen urea. That is the waste product of proteins. I just circled it. You'll see uric acid looks an awful lot like a purine nitrogenous base, so it would make sense that this would be a waste product of nucleic acids. And then down here you see ketone bodies. So ketone bodies are just the name that we apply to a collection of molecules that all have a ketone in them or something very similar to a ketone. You'll notice that two of them are acids. So this ends up being kind of important. We have an acid and an acid. So two of them are acids. So what does that mean? That means that potentially if ketone bodies become too numerous in the bloodstream before your urinary system has a chance to appropriately excrete them, you could be dumping extra acid into your blood, which would reduce the pH of your blood and cause acidosis. So ketone bodies are the products of lipid metabolism. So what I would like to do now is actually talk a little bit more about acidosis, something that was mentioned briefly when talking about Lab 20 and the acid-base balance of the blood. And now we're going to bring in ketone bodies into that discussion. So acidosis is obviously the drop of blood pH. So blood pH becomes too acidic. There are two major types of acidosis: respiratory and metabolic. All right. Respiratory acidosis is caused by an accumulation of CO2 in the blood that is not appropriately excreted by ventilation. So there are a number of things that can cause respiratory acidosis, but it effectively describes a mismatch between your ventilation patterns and your CO2 production. So one example of that would be hypercapnia that we looked at in Lab 20. But any disease that severely impairs ventilation, and COPD, or chronic obstructive pulmonary disease, I'm looking at you, would also or could also result in respiratory acidosis if it's severe enough. Again, the idea is you produce a certain amount of CO2 and your ventilation pattern should match your CO2 production to appropriately excrete that CO2. So if your ventilation does not secrete enough of that CO2, then the CO2 stays in your alveoli, which means that it builds up in your blood. And if it builds up in your blood, we know that excess CO2 combines with water, produces carbonic acid, and brings the pH down. So how can you deal with respiratory acidosis? Well, the obvious answer, it may not always be feasible, but the obvious answer is simply to adjust your ventilation patterns to appropriately excrete the excess CO2. Okay, so let's look at metabolic acidosis. In metabolic acidosis, you have an accumulation of acid from some sort of metabolic byproduct, and that usually is the ketone bodies that are produced because of excess lipid metabolism. Now, you're breaking down fatty acids and fats in your body all the time, and so you're constantly dumping ketones into your blood, but you're dumping a relatively small amount of them, an amount that your urinary system is capable of keeping up with. If something were to change and suddenly you started metabolizing a lot of fatty acids, way more than you typically could or should, then you would have an abundance of ketones that would be dumped into your blood. Two of those ketone bodies are in fact acids. So you would basically make your blood more acidic from an overwhelming number of ketone bodies in your blood. This is sometimes referred to as ketosis, just means the accumulation of ketone bodies. But the danger of ketosis is that it can send you into metabolic acidosis. Now, metabolic acidosis could be more severe than respiratory acidosis because there's no quick fix. Unlike respiratory acidosis, where if you change the ventilation pattern, you should deal with the extra CO2 rather quickly, like within a couple minutes, metabolic acidosis relies on the urinary system to flush the excess ketones out. So you have to wait on the urinary system. Interestingly enough, if somebody has metabolic acidosis, they might actually invoke their respiratory system to help them out. So one of the symptoms of somebody who is experiencing metabolic acidosis is panting. Like, I'm just sitting here at rest and I'm panting. Well, that's hyperventilation. What they're actually trying to do is get rid of extra CO2. By getting rid of extra CO2, that takes some of the existing H+ that's in the blood because of the ketone bodies, recombines them with bicarbonate, reforms carbonic acid, splits back into CO2 and water, and therefore sucks up the hydrogens out of the blood. So in other words, you invoke the respiratory side to try to deal with the metabolic side. So you're going to increase your respiration rate in hopes of clearing more CO2 out than you typically should, in hopes that that actually converts some of the existing bicarbonate and H+ that's in the blood back into CO2, and thus sucks up some of the H+ that's in the blood that was put there by the ketone bodies. So the respiratory response is an accommodation to metabolic acidosis, trying to help you out. But the cause of metabolic acidosis is usually an increase in ketone bodies. So if metabolic acidosis is ultimately caused by excess lipid metabolism, then what causes excess lipid metabolism? There are a number of causes to excess lipid metabolism, including diabetes mellitus, which we'll be covering later on, and a no-carb diet. So no-carb diets are well established as a way to quickly lose weight. When you stop eating carbohydrates, your body runs out of its favorite fuel source, and so it can go through a process called gluconeogenesis. Gluconeogenesis, I'll go ahead and write that down. The word gluco means glucose, neo means new, and genesis means to create. So to create new glucose. Gluconeogenesis is the process of taking other substrates and refashioning them or retooling them into glucose. So if you're not eating your glucose, then you can actually take lipids and sometimes proteins and remake them into glucose. This is done predominantly in the liver. Okay, if you do that, lipids are usually your first choice. So you'll go to lipids first. So if you run out of glucose because you're not eating it, then you'll go to the lipids and you'll suddenly metabolize all of these lipids to remake glucose. Well, that produces a bunch of ketone bodies all at once. So people who just start or are on a very, very strict no-carb diet are going to have excess lipid metabolism because they have to create their own glucose. Of course, it melts the fat away, and that's one of the desired outcomes. If you go overboard on that diet, you have a risk of running into ketosis and metabolic acidosis. All right, now that we've gone on that little tangent, let's come back up over here to the biomolecules. There's one more that I want to talk about. It's a special one. It's not part of the carbohydrates, proteins, lipids, or nucleic acids. It's actually a protein. but it's abundant and we break it down a lot, and that is hemoglobin. So remember, in an earlier lecture, I mentioned that red blood cells get funneled into super small capillaries in the spleen, and the red blood cells have to kind of shrink down and expand back out. And if they fail to do that, they lyse. And of course, that's going to release about 250 million hemoglobin molecules. So those hemoglobin molecules are scrounged up by the liver and then broken down into something called bilirubin. And then the bilirubin is excreted. So let's add that. Now, where is that bilirubin excreted? Well, the bilirubin is excreted in both the urinary system, it's actually the major site, and also the digestive system as a secondary site. So let me write this down and then we'll talk about it. So there's actually a couple different forms of bilirubin, including one called a urobilinogen. And the word uro stands for urine. That's the form that gets dumped into the urine. There's actually a form that has an affinity for urine and a form that has an affinity for, or is dumped routinely into the feces. Okay, so the liver, as I mentioned, is responsible for collecting the excess hemoglobin out of the blood and breaking it down into bilirubin. Some of that bilirubin is going to get dumped back into the bloodstream. All right, let's take a look at hemoglobin, bilirubin, the liver, and these two systems. So the liver there's my liver, is going to be very bloody. You might remember that from anatomy. So it gets a lot of blood. So blood's going to come by my liver. And there's hemoglobin, free hemoglobin that's been released from lysed red blood cells. So remember, hemoglobin is this 4-unit molecule. So the liver is going to pick up these hemoglobin molecules and start breaking them down into bilirubin. So the liver is going to break them up into two different forms of bilirubin. I'll just say B and B naught. B naught, which is like the urobilinogen, is going to go back into the bloodstream. And once it goes back into the bloodstream, it is likely to be excreted out via the urinary system. So we'll make it yellow because in fact that bilinogen has iron in it, and that iron, that metabolized iron actually, is what makes the urine yellow. If you've ever wondered why is urine yellow, it's not because of urea, it's because of the bilirubin byproduct that is made. Now the other form is going to get dumped down the bile duct. And if you remember anything from your anatomy class, you know that the bile duct is going to lead into the duodenum along with, pancreatic secretions. And so this is all going to go right into your small intestine, where then that molecule is just going to run all the way down to the large intestine, and then it will become part of your feces. So some forms of bilirubin are dumped down the bile duct into the duodenum of the small intestine, where they will eventually become feces. And interestingly enough, this contributes to the brown color of feces. Without bilirubin, feces would be more of a grayish color like bird poop. There's your fun fact for the day. Okay, so I can't believe I'm really going to do this, but we'll draw our little bile duct. All right, we've covered the biomolecules, we've covered their waste products, and now we've covered what systems are primarily responsible for their excrement. So you'll notice the urinary system is the big one. So one of the major functions of the urinary system is in fact waste excrement. Of course, it's not the only function. So let's list a couple other functions, and then we're going to end this mini lecture and pick up with the next one. So what are some functions of the urinary system? All right, waste excrement is certainly a big one. Probably the biggest and perhaps most important ones are water and salt balance, or water and ion balance. So you know that if you drink too much water, you're going to pee a lot. You know that if you don't drink enough fluids, you're going to be dehydrated and you won't urinate very much at all, and the urine that you do produce will be extremely concentrated. So clearly the urinary system is recognizing that you have too much water, get rid of the excess, or you don't have enough water, keep it, don't pee out too much. So that's all part of your water balance. Similarly, the urinary system is responsible for making sure that your extracellular fluid ion levels are maintained at appropriate amounts. So what are the big ones that we need to look at? Well, sodium and chloride, and then also potassium. Now, potassium is not normally an ion that's concentrated in the extracellular fluid, and the urinary system aims to make sure that it stays that way. Because if you have too much potassium in the extracellular fluid, you ruin your electrochemical gradient, and things like action potentials are not going to occur. So it might not surprise you to learn that when you talk about lethal injections, it's actually a series of injections. And the third and final injection is potassium straight up into the extracellular fluid around the heart. That ruins your chemical balances and your heart stops because potassium is not being pulled out of the cell when the potassium gates open, because there's plenty of potassium outside of the cell. So it's really important that your urinary system keeps the potassium levels in your extracellular fluid low. Okay, so those are kind of the major functions of the urinary system. Waste, maintains water levels, and maintains ion levels. So with that, we're going to go ahead and stop this lecture, and then we'll pick up on the next lecture, starting to look at the anatomy of the urinary system.